Let's use our understanding of acid-base chemistry to investigate what happens in pure water. Two water molecules can react with each other and produce H3O plus and OH minus. So in this case, one of the water molecules is acting as an acid and the other water molecule is acting as a base. One water molecule has donated a proton to the other water molecule, it's the acid. The other water molecule has accepted a proton from the other water molecule. When the acid water molecule donates its proton, it becomes OH minus. And when the base water molecule, the one that's accepting the proton, accepts the proton, it becomes H3O plus. And so we can see that this is a conjugate pair and this is a conjugate pair. So this is the water molecule without an extra proton, and this is the water molecule with an extra proton. So this is the conjugate acid of this conjugate base. This is the water molecule with a proton, an extra proton, over the OH minus. The OH minus is missing one proton relative to this water. So this is the conjugate acid, it has the proton, and this is the conjugate base, it has lost the proton. Recall that a molecule that can act as both an acid and a base is called amphoteric. And so water is amphoteric. And this reaction is known as the autoionization of water, and it has an equilibrium constant that is designated by Kw, and the W just stands for water. This equilibrium constant is approximately equal to 10 to the minus 14 at room temperature. And it would be important for you to remember that number, because that number becomes really important. Notice that the equilibrium expression for Kw is based on this reaction. And water is a pure substance in this reaction, so it has an activity of 1. And so the equilibrium constant expression is just going to be the concentration of H3O plus times the concentration of OH minus. And because that product must always equal 10 to the minus 14, it equals a constant, we can see that if we increase the H3O plus concentration, we must decrease the OH minus concentration. Likewise, if we increase the OH minus concentration, we must decrease the H3O plus concentration. The only way to have that product remain constant is that if one increases, the other decreases. If I use my P scale, my minus log scale, to represent the H3O plus and the OH minus concentration, I can use this equation by taking the negative log of both sides of this equation. So I would have minus the log of Kw is equal to minus the log of this product, H3O plus times OH minus. Remember that in our rules for logs, that if I have the log of a product, it's the same as the log of the first thing plus the log of the second part of that product. And so this can be written as minus the log of H3O plus concentration plus the log of the OH minus concentration. Now notice that if I distribute this negative sign, that minus the log of H3O plus is just the pH, and minus the log of OH minus is just the POH. And so I can write that minus the log of Kw is equal to pH plus pOH. But minus the log of Kw is minus the log of 10 to the minus 14, and that is just equal to 14. And so a very important equation that I might want to remember is that the pH plus the pOH must always add up to 14 when I'm in aqueous solution.